So my name's Eric Redmond. I am here working at, I work for Basho, which is a company that makes Riak, which some of you may have heard of. It's a open source distributed database lumped into the NoSQL family of databases. I've also written a couple books, 7 Databases in 7 Weeks, where I just kind of did a synopsis of 7 different styles of databases, from relational to document stores like Mongo and all of these. And then one of those databases was Riak, and I was so interested in the technology, and I was just so enamored with how elegantly it was designed. I kept doing talks trying to promote my book, saying how great Riak is, and I was doing it so much, Basho decided to start paying me to do this. So I appreciate that, guys, because I was going to do it anyway, so thanks for the paycheck. But I ended up writing another book most recently called The Little Riak Book, and if you go to littlereactbook.com, you can get a very short overview. It's about 100 pages. It's free to download, PDF and Kindle and all of this. And then as far as the 7 databases one, you have to buy it, but I am told that you can get it on BitTorrent. So, go ahead and grab it there. I don't really mind. I really would just rather have people read it. Am I too far or too away? How about now? Can you hear me? All right. So one of the things that I really wanted to talk about, the title of this talk is Riak Built Distributed, and I really wanted to put forward this thesis out there in NoSQL, about NoSQL databases, that they're all built for high scalability and all of this. And I think architecturally, and what's lost there is architecturally, there are sort of 2 different philosophies that come about in these building these databases. There is the sort of classic model where you take existing databases like MySQL and then you distribute them in some way. You'll try to build a cluster, but it was initially designed to stand alone on one system. Then you have a totally different philosophy espoused by like Riak and Cassandra and HBase, where it's never built to run as one single server. It was actually built as a distributed system, and it almost just so happens to have persistence and query mechanisms on top of it. But the distribution part of it is the more important piece. Now, we do hear the word distribute a lot, and what I have up here is just the assumption that, okay, we're going to start with 3 nodes, and I'm going to use this as a visual aid throughout this talk. But you always have to start saying, well, why? Why do we want to distribute our data? Is it for fault tolerance? If one goes down, can we continue running? Or are we doing it to expand resources? You can only build single machines so large, so we can distribute it in that way in order to expand these resources. And then you say, okay, well, we want to handle more resources, but why? Are you trying to handle higher loads? Fine. What do you mean by handle higher loads? Are you talking about more reads? Are you talking about more writes? Because the answer to that question will change how, again, you build your network topology. So we'll start with the sort of most basic case of distributing a database, which is if you want to expand resources, you're going to do what's often called sharding. And sharding is basically the act of taking a single class of data. In the standard relational case, we might say a table, or in the case of Mongo, it would be a collection, and distributing parts of that entire data set across multiple systems. And it's really simple to do. But the problem is, it also increases risk. I mean, think about I think it's RAID 0 that is just effectively straight data stripe. It's just striping data across disks, and there's no replication. It's just pure data striping. And let's say the odds of one disk failing is 1%. It seems like it's safe enough, but if you have 67 disks, the odds of any one failing is 50%. I mean, that's a coin flip. One of those disks is going to fail. And if all you've done is just shard your data across all of these disks or all of these nodes, and you lose one with no backup whatsoever, I mean, you have corrupted your data. So when splitting data, you get access to more resources, either more disks or more CPU if you're sharding across multiple machines, but you also increase your risk. The other reason that I mentioned people want to distribute is for fault tolerance, and the solution for that is just replication. You know, we replicate data to handle faults. It allows us to expand resources for read operations as well, or we can divide up tasks across duplicate nodes, such as certain aggregate functions like counting and grouping or anything else you could do with MapReduce or Hadoop or whatever. But there is a downside, and most of the time when you hear about problems that come from distributed systems, yes, sharding increases your risk, but replication is really where most of the problems come into, because you always run the risk that data that is replicated to two different nodes will get out of date. Something could happen to a node mid-write even, or your network could partition. Now, some people say, well, you know, network partitions are rare and all of my servers are co-located and I'm not going across data centers. What could actually happen? Well, the problem is that most network partitions aren't accidental in any sort of physical sense or something breaking. It's usually you that causes the problem. I mean, not you guys because you're smart, but somebody who's less smart in your company is going to update IP tables incorrectly, or they're going to trip over a network cable, or somebody is going to try to fix the plumbing behind your building, and a backhoe is going to rip out a T3 line. I mean, there's all sorts of reasons where servers can stop communicating with each other, and you know, it's sort of what's generally encompassed in this thing called the CAP theorem. Is everybody here familiar with the CAP theorem? Okay, so about 6. All right. Well, so I will go over it really, really quickly, but it's a really simple concept, actually, is CAP theorem, C, consistency, A, availability, P, partition tolerance. When I talk about consistency, I mean that any read is going to be consistent across the entire system, or any write is going to be consistent across the entire system for subsequent reads. So if I were to write a value to node A, and then I read immediately after from node B, B is going to have that value. The entire system will give me the same answer no matter what node I talk to. Availability is the ability to respond to to respond to requests. Every time I ask a node, if it's running, it should give me an answer. That's availability. Partition tolerance is when I mention a network partition, it's tolerant to handle network partitions. And I've got a little thing at the bottom here. You can't really read it, but I think we'll have these slides available. Coda Hale did a fantastic write-up a while called "You Can't Sacrifice Partition Tolerance." This theory that somehow you can build a distributed system that is impervious to network partitions is just insanity. Don't listen to a single person who says that that is the case. Well, it can actually be both. I mean, and like I said, you could even have a multi-core system where if you're using Unix sockets or something to communicate between individually running processes, somebody could mess something up. I mean, it's an imperfect world. There's always a reason why processes couldn't communicate with each other, and then in which case they can get out of sync. Now, so the P is something you can't sacrifice. So P basically means, is this a distributed system that's running with multiple processes? And most of the time, is it running on multiple servers? So you have to choose. You only have 2 of these items: consistency and partition tolerance, availability and partition tolerance. And I have a little story that I like to help explain this. So say that you've got 3 men that are sitting at a bar ordering drinks. And a bartender comes up and he gives all 3 of them a beer. And if you were to ask any one of them, what was the last drink that you all had? The answer, any one of them will say, I just had a beer. Now, one of the men gets up and walks off to use the restroom. He's partitioned from the other 2. He can't talk to them. This is a network partition. So now, say you follow the man to the bathroom in a not creepy way, and you ask him, what was the most recent drink that you guys had as a group? While he's gone, the bartender gives the other two guys whiskey. So the problem now is the guy could give you an answer. He could say beer, but he would be wrong because it would be inconsistent from the same question I were to ask the two guys sitting at the bar, because they would say the last drink we had was whiskey, not beer. So that's an inconsistency. The other option is he could just refuse to answer and say, you know what, I don't know. I'm partitioned from those guys. Things may have changed. I can't guarantee that the answer that I will give you is the same as them. So he's preserved the consistency, but he's just made himself unavailable to answer that question. So that's sort of the essence of the CAP theorem. You can have one, consistency, availability. You can't have both. This is our original 3 nodes, and this is sort of the classic way of distributing a system where you've got your, so I've got, at the top says P, and the second S for secondaries. Also master-slave is another name for it. So in this way, they attempt to keep consistency by saying, I'm just going to communicate with that first server. Say it's a MySQL database, or Mongo. Mongo does the same thing with replica sets. And then this happens. A partition occurs. The master cannot communicate to the secondaries anymore. It can't replicate those values. So what you can do is say, okay, I'm going to elect a new master. That's the one that I'm going to talk to. And that first master just becomes unavailable. It's in the minority of the partition. And this is what Mongo does, is where it says, okay, it's going to vote on a new master and say, since this old master can't, since it's only one it can't communicate with the other two, it's just going to refuse requests. It is unavailable in an attempt to keep consistent. That's one way of doing it. The problem is that when we heal the network and then say that we re-elect that master, it is possible that rights could be lost, because in between these two, this guy may have accepted some rights. He then decides, oh, wait, I can't communicate with the other two, and these guys aren't necessarily up to sync. So what you end up still is with an eventually consistent system, which is not actually consistent. Eventually consistent is sort of the way we get around the fact that we can't do full consistency. And anybody who's done this with a relational database where you just have a backup, and say you back up every minute or something, and your main server crashes. Yeah, you might have full ACID transactions, and you think that's consistent, except now that your primary server has crashed and you go to reload that data, you lost a minute worth of data. That's not really very consistent, is it? I mean, you just can't beat this CAP theorem if you want to remain available. So anyway, this was the thesis that I originally said that I wanted to go over, that don't distribute data stores, store distributed data. Meaning don't convert single node databases into distributed databases. Instead, build a distributed system that can store data. Which brings us to Riak. So let's start with our 3-node system and do the simplest thing. We want to expand our resources, so we're going to do sharding. We're just going to say, okay, I have a key space. Any value that's keyed from A through I gets put in this one in node A. Any with J through R gets put in B, and any with S through Z gets stored into server Z. And each server knows whether it should store that value or not. And if not, then it'll just refuse, or we could even put a little router that will reroute to the correct one. The problem is, if we were just to simply do this with a hash, does everybody understand the concept of a hashing algorithm, where you'll just take a key and you convert some sort of number or some other value that you can put in a bucket? The problem is this: if you just have sort of a naive hash where you're keeping track of what values go into which of these servers, if I add a new server, I have now changed my algorithm. Because before, the number 4 may have been put in bucket B, and now after I added D, it goes into A. So especially if you're doing this as like a caching system, you have invalidated a ridiculous amount. And this is just a little example that I did, taking a naive hash, putting 100,000 values in it, adding a new node, and then seeing, what's my miss percentage, and it was 90%. 90% of the values are now invalidated because they don't actually live in the servers that I expect them to. So anyway, we use this thing called consistent hashing. which effectively divides up a key space into different partitions, and then it assigns parts of these partitions into different nodes. And the nice thing about this is if you sort of, you can't really see the colors very well, but it's yellow, green, blue, and it counts around and says, okay, the yellow partition goes to the first node 0, green goes to node 1, blue goes to node 3, and then it starts counting on and on and on. The benefit here is that when you add a new node, if you can see the red, I have, most of them remain the same. They only have to share, they only have to transfer a little bit of data over to the new node when it happens. And if you run this exact same algorithm on the left-hand side, this was an implementation in Ruby of a consistent hash, but my miss was only 9%. So it's nice. So we've easily built a little data structure that allows us to keep track of what value goes where.
Eric?
Yes, sir.
What changed from the first one, there was a 90% loss, to the other one, there was 9%? What was the difference?
The difference is this. Rather than doing this naive hash where we just have an array of values that
It's still effectively modular because you're still just round robining from one store to the next.
But it's not, because rather than one node having a single span of contiguous values that it keeps track of in the key space, in this case, it skips, it alternates, and it takes chunks of them and assigns them to different nodes. So the nice thing is we can skip around and keep most of them the way they were without actually having to change what nodes are responsible for what parts of the key space. Anyway, there's interesting articles about the mathematics behind it. It actually, anyway, you will always have far more partitions than you actually have nodes in practice. Usually we say about 12, 10 to 12 is a pretty good ratio. Well, that's when we do repartitions, and that's actually something available in Riak 1.4, where you can actually add more vnodes. But anyway, so moving on to the next part. So what we had before was great, except for the fact that we would have to know, our client would actually have to know where values live in the system. You'd say, okay, well, I'm going to write Apple. Well, that goes in node A. That's a lot of burden to place on a client. So what we do is we just have the nodes communicate with each other, and one node will act, whatever node you talk to originally acts as the coordinator. And it'll say, okay, I wrote to A. If I want to pull from C, it's fine. It'll just go to A, grab the value, and then return it for you, which is just one network hop because it's actually a mesh network and all of the nodes are aware of each other. It basically acts like a client on your behalf. Yes, sir. No. You don't do anything. You just talk to any random node. Usually the clients will round robin between, around nodes. It adds one hop. And that you don't know. No, it's completely opaque. It's a cloud. You just connect to any node. It doesn't matter. And then if it happens to live on that node, it will just say, okay, here's my value. If it doesn't, then it internally knows where the key actually lives, and then it will communicate with that server on your behalf, grab that value, and then return it. So it basically acts as a router at that point for you. I mean, so you're not losing anything. I mean, under normal circumstances, I mean, think of like if you're familiar with Mongo and you do sharding, you actually communicate with a server called MongoS, which then itself keeps track of where all the shards are with a different set of servers called configuration servers, and it still has to do that hop. I mean, anytime you stick a router in front of these databases, you're still adding a hop, so you're definitely not losing anything. It's just doing the routing for you.
Going to a specific IP address, and then
Anyone, you know the IP address of all of your nodes, and you can just connect to any random one, and you will get the result no matter what. Well, yeah, that's what I said. When you are writing your code, you will just give the list of all of the nodes that you're aware of, and it will round robin its connections. So it won't keep hammering one node. It'll go node A, then node B, then node C, and around. Or you can put your own router in front of it too, and let it handle and have your client connect to that. I mean, there's multiple ways of doing this. So we've sort of solved that problem, but I'm gonna skip cluster changes because we're running late and it's not actually that interesting. But here is something that is interesting, and this is when we're replicating values. So far all we've done is we've just sharded our data across multiple machines, but we still haven't fixed the problem of what happens if one of those nodes goes down. We've lost that key space. We've lost all of those values. So we resolve this by then adding in replication as well. So when you write to one node, it'll then do what's it'll look for the next contiguous nodes and then replicate it to that one and then to the next one. So in this case, if we were to put some value into node A, it would then, if we had a 5-node cluster, it'll then also replicate it to node B and node C. This is called the N value. And if you've ever read the Amazon Dynamo paper, there's the N value, the R value, and W value. N is the number of nodes you want to replicate to. It's generally 3, but it can be any number you want. I mean, you could actually replicate a value to all of these nodes, in which case you just have a fully replicated, you just have a whole bunch of nodes that have replicated everything. So now we have a different problem, though, because we fixed the problem of losing data when nodes goes down because we replicated, but now we have a problem because nodes can always conflict. This is an issue. So say we have two guys writing to two different nodes at the same time with the same key. But they've given them different values. In this case, say apple is red, and the other guy says apple is green. And then when I go to read from node A, and it's tried to converge them, which one wins? A simple answer would say, oh, we'll just add a timestamp. And some databases do this. But anybody who's ever been an ops person for a distributed system knows you can't really rely on timestamps when you have multiple servers. You just can't keep them in sync, and you not well enough that you can rely on it as being any sort of canonical thing. So, but there is a better solution. Rather than having timestamps as far as what we think of as time, you have a logical timestamp, which is just an ordered list of operations that have occurred on it. And so this is sort of a simple example where Adam says, okay, I'm gonna set what are we gonna eat for dinner? He's gonna set the value pizza. And in his logical clock, called a V clock, a vector clock, he's going to add himself with the number 1 and say, I am saying I want pizza. At the exact same time, Barb says, I want tacos, and she's going to add herself. What happens is the next request, since these V clocks don't actually descend from each other, and when you think of dissension, think of it in similar terms of something like GitHub or MVCC with Subversion, where there's a list, a logical ordering of operations. But sometimes you have conflicts. And when you have a conflict, what do version control systems do? They give you the changes. They say, hey, I don't know how to resolve this. There's conflicting changes. 2 different people want to make a change. I don't know what to do, so here are both of the values, and it's up to you to actually have to resolve it. Riak does the same thing, because it's not going to try to guess for you. So it's going to return both values. And so Adam goes and pulls this and says, you know what, fine, I think what we should do is have taco pizza for lunch, which if you've never had taco pizza, I highly recommend it. It's absolutely delicious. But then what it'll do is he'll then update the V clock with himself as well, and he's resolved this conflict. So now successive requests will just go back to returning 1 value. So we're done, right? You know, we shard our key space to horizontally scale, replicate values for consistency, and vector clocks to resolve conflicts. The problem is that this can always happen. Because what if a node misses a write? What if I wrote apple to be red on all of these, and then then this node dies and somebody sets green, and then now B, when I turn it back on, it still has red because it's wrong. So we have 2 ways of dealing with this. One is called passive anti-entropy, and and the other is active anti-entropy. Passive anti-entropy is something called read repair, and so I'm not going to go over all these steps. We're running out of time. But basically, what happens is the interesting thing is on step 3 here is when you get a request. In the background, it will communicate with other nodes that it knows has a replicated value and then attempt to see to make sure that it has the most recent value. If it doesn't, then it'll repair itself, so on subsequent requests, it will have the most recent value. This is an eventually consistent system, and all we guarantee is eventually they will converge to being consistent. But that's also a lot of overhead, and we don't want to have to wait for this to happen. So we have the other thing called anti-active entropy. And basically what this is it's a better system that uses something called the Merkle tree, which is data structure, which is a tree of hashes. And what it'll do is it'll pass levels around actively in the background, like every minute, and say, hey, is this level of hash exactly the same as what your level of hash is? If it's not, you know that somewhere underneath that tree is a level where something has changed. If it is, you're done. You're just like, okay, I'm consistent. But if there are differences, it'll just keep walking down the tree until it finds exactly what those differences are in the key space, and then it'll repair for you. And this is really, really nice. Anybody who's done any sort of operations with databases before would have had a database crash, and then you have to run repair operations. Active entropy actually resolves this because all you have to do is turn that node on and then just wait, and it'll fix it in the background. And then, finally, all we've done is key values, which are no fun. So we've also implemented MapReduce. So say these are all values of fruits, and I want to make a fruit salad. All I do is implement execute MapReduce. Nice thing about MapReduce is you can distribute it, the mapping and then the reduction across multiple servers, so that you actually do aggregated queries, which is something you can't generally do with a strict key value store like a Memcache or Redis or something like this. I think I have overstayed my welcome. So just one last thing. Oh, actually, nope, that is it. Thank you.